Hello mga kabulero. This is the other part of our discussion on linear support vector machine. You're watching this video because you are interested of learning the mathematics behind the machine learning algorithm. So let's first define SVM. So a support vector machine, or SVM, is a supervised machine learning algorithm that can be used for both classification and regression tasks. In SVM, we plot the data points as points in an n-dimensional space, n being the number of features you have, with the value of each feature being the value of a particular coordinate. So the classification into the respective categories is done by finding the optimal hyperplane that differentiates the two classes in the best possible manner. And in our example, in our project, we have determined that we only have two classes, and L-SVM is perfect for these kinds of scenarios. So to understand the model, let me show you a simple approach on how to compute for the hyperplane to separate the given data points. By the way, hyperplane can be considered decision boundaries that classify data points into their respective classes in a multidimensional space. So data points falling on either side of the hyperplane can be attributed to different classes. Suppose we have two different classes to identify and separate. Let's say class 1 corresponds to all positive data points, and class 2 corresponds to all negative data points. At a quick glance, it is easy to say that hyperplane is lying parallel to the y-axis in between 1 and 2. But let's proceed to the next steps to compute mathematically. So our given points here before we proceed to the next slide, we have for class 1, we have the coordinates 3, 1, 3, -1, 6, 1, and 6, -1, provided by the blue dots. And for our class 2, the red dots, those are represented by the coordinates 1, 0, 0, 1, 0, -1, and -1, 0. So the next step is to determine the support vectors. And what are these support vectors? Support vectors are the data points that are closer to the hyperplane and influence the position and orientation of the hyperplane, because not all hyperplanes are parallel to the y-axis or parallel to the x-axis. Most of the time, hyperplanes are slanted, and these are on this picture designated by the amber colored points on our plane. By the way, it's not yet the hyperplane, but those are the support vectors. So using these support vectors, we maximize the margin of the classifier. Deleting the support vectors will change the position of the hyperplane. These are the points that help us build our L-SVM. So note that one support vector in this image or in this slide is from the negative class, and that is S3. And two of the support vectors are from the positive class, which are the S1 and S2. So each support vector is augmented by a bias input of 1. You can find this bias on the third row of each vector. Therefore, the new variable for the augmented support vectors are now S1 curl, which is 1, 0, 1 in matrix form. S2 curl which is 3, 1, 1, and then S3 curl is 3, -1, 1. We also have introduced here three different constants. We have A1, or not variables, three different variables, A1, A2, and A3. And these are constants. And later on, we will compute each of these constants or variables because it is very important to complete the working equation by the following or by following the indicated operations. So our goal here is to make sure we got all the necessary data for our working equations, such as A1 multiplied by S1 curl dot, doing the dot product of the first term, A1 S1 curl dot S1 curl plus A2 times S2 curl dot S1 curl plus A3 multiplied by S3 curl dot S1 curl is equal to -1. The next equation is A1 S1 curl dot S2 curl plus A2 multiplied by S2 curl dot S2 curl plus A3 S3 curl dot S2 curl is equal to +1. And this is the next positive support vector from what we have discussed earlier. And the last support vector, which is the other positive, is A1 S1 curl dot S3 curl plus A2 multiplied by S2 curl dot S3 curl plus A3 S multiplied by S3 curl dot S3 curl is equal to +1. By the way, you can read all of these A's can be an alpha, alpha 1, alpha 2, and alpha 3, but it depends. So after realizing those previous equations, we can now obtain the results. And here are the results after getting the dot product of the 1/3 matrices and its sum. So from the generated equation, we can solve the problem, the values of the introduced constants, which are the A1, A2, or A3. So if you forgot the basics of doing the dot product, you can refer back to your discussions from advanced mathematics or other mathematical areas which has the discussion of the dot product. And this is very simple because it's just 1/3 matrix multiplied by a constant. So applying the indicated operations here, A1 is equal to -3.5, still a negative number. A2 is now equivalent to 0.75, and also A3 is 0.75. So for linear model, the hyperplane equation looks the same as the slope of the line equation. It is very nostalgic. The slope of the line equation is y is equal to mx plus b, where, m is the slope and b is the y-intercept. So what the weight vector signifies is that the hyperplane is parallel to the y-axis, given the coordinate -1, 0. So if we plot the hyperplane, this looks like this. There you are. So the bias, which is -2, and that is the y-intercept, right? That is the distance of the hyperplane to the y-axis. Given this, here is the y-axis, and you got the hyperplane at 2. So the negative means that the y-intercept is on the left of the hyperplane. So this graph shows you the position of the hyperplane in such a way that the margin between the hyperplane and the support vectors is maximized. And that is the main goal of SVM, which is to maximize the margin to avoid misclassifications. So just think of this as the red dots are the class 2 of our Peely sorting project. These are the class 2, and these blue dots are the class 1. And this hyperplane is very significant so that the prediction of the classes from the testing images will not merge, or misclassifications will be prohibited. Now, To give you the results from our Matlab project using L-SVM, let's move on to the next slide. So here's the statistics of the extracted training data from the Pili Fruits sorting project that I have created. Just to share some of the terminologies, IM mean is the mean of the binary image. IM STD is the standard deviation of the binary image. And for classes, we have class 1 will be which is the unripe Pili Fruits, and class 2 will be the ripe Pili Fruits. Let me show you the actual view of the extracted features of the database in Matlab, and you will see different columns on our Matlab project. So going back to our database, just let us load the database in Matlab. There you are. And go to workspace, and let's see the matrix. All right, so column 1 is you will find the mean of the extracted features from the binary image. So these are the test images that we have shown you in the previous video. This is column 2 is the standard deviation, and column 3 is the trained classes that we have determined from our training images using the training code. And that's how the matrix looks like. And that's how the computer works and how the computer sees the images. It is converted into a binary image or binary numbers in matrix form. All right. And finally, here is the model's outcome and performance review. The significant margin or gap between the parameters of the sample data will justify why the L-SVM delivered exemplary results in classifying the maturity of the pili fruits. So the numbers provided here were gathered from 200 images to train the model, and the scatter plot of the data is shown on this slide. Notice that we have the red dots, we have the blue dots, and that's just to signify that we have two different classes. Those red dots are the unripe pili, and those blue dots corresponds to the ripe pili. So 9 out of 200 samples were misclassified during the validation, having an average training accuracy of 95.5%, which is still a pretty good number or pretty good model accuracy. And additionally, it took 6.19 seconds to complete the training validation. So this is the end of this video, and I'm hoping you learned a lot from this presentation. Watch out for more discussions on image classification and machine learning. Thank you very much.